Welcome back. Today we will discuss about the residual life, age and duration of a renewal process, only restricting to time averages. Okay. So, before we get into this, I would just like to refresh your memory on the difference between the time averages and ensemble averages. Just recall that if NT is a renewal process, we looked at strong law last class, right. This is where we left off. Strong law says that limit t tending to infinity nt over t is equal to 1 over x bar almost surely. So, the strong law is an example of a time average statement. So, just to draw some pictures for you. So, let us take, so let us say this is nt over t. So, nt let us say for a particular omega 1 over t against t, all right. So, this will look like, so this horizontal axis is time, okay. So, it will look like jump, decay, jump, decay, jump, decay and so on, right. This is, so wherever you have an arrival, you the nt over t jumps, right, by 1 over t whatever the time is, and then it decays until the next arrival, there is a smaller jump and so on. So, what we are saying is that this as t becomes very large, this sample path nt of omega 1 over t settles down at 1 over x bar for almost all omega, right, which means on a set of little omegas whose probability is 1, we have nt omega over t converging to 1 over x bar, right. So, for very large values of t, you will see that this converges to 1 over x bar, right. So, if you look at a different sample path, let us say some omega 2. So, this let us say nt omega 2 over t, you will have a different sort of a I mean essentially same kind of a qualitatively same kind of a sample path, but it depends on where the arrivals occur, right. You will have something like this, and then for let us say for another omega 3 you have something else, right. You may have and so on, right. So, this is for nt omega 3 over t versus t. So, what we are saying is that the set of little omegas where these functions nt little omega over t does not converge to 1 over x bar has probability 0, okay. On a set of probability 1 we have convergence to 1 over x bar, right. So, this is what we mean by almost shear convergence, and this is what the strong law says, all right. So, this is a typical example of a time average, okay. You take average over time nt over t, the average arrival rate, right, and you say that this goes almost over almost all the sample path to 1 over x bar, okay. There is another very important theorem which is known as the elementary renewal theorem, which says that limit t tending to infinity expected nt over t is equal to 1 over x bar, okay. So, this is an example. So, the expectation of course can be I mean you can put the t inside the expectation because t is not a random variable, right. So, you can write it as expectation of nt over t, nothing wrong with that. By the way, so this limit is not almost surely or anything, it is like expectation of nt over t is a, for each t it is a number, right. So, it is just convergence of some numbers, some sequence of numbers, right. The sequence is indexed by t, that is all. Okay. So, this is a I want to say that this is in terms of meaning it is very different, okay, that I want to first convey. The second thing I want to tell you straight away is that the elementary renewal theorem is in no way a consequence of strong law. It looks as though, I mean, what is the big deal, right. It looks like if NT over T goes almost surely to 1 over x bar, the expectation you might think should go to 1 over x bar. It is absolutely not true. If your sequence of random variables converges almost surely to x, it is absolutely not true that expectations converge, okay. And in any case, proving the elementary renewal theorem is much harder than proving the strong law, okay. We need to build up some more machinery to do that. So, the two things I want you to recall, so remember now, is that elementary renewal theorem is a completely different result, no way a consequence of strong law. Second, I want you to understand that it means something different from strong law. Strong law is just time averages, like as I have drawn here, okay. So, when you take expectation, okay, so you can think about it like this. Expectation is a, so informally you can say that expectation is an ensemble average, okay. By ensemble average we mean we are averaging over various realizations of the process, okay. So, you look at, let us say you fix a large t, okay, let us say you fix some particular some particular time, I am okay, let us call this t naught, okay, let us fix a time t naught, let us say, which is large, okay. You know this, you are looking at expectation of n t naught over t for large t naught in the elementary renewal theorem, right. So, what you are doing is that for this particular for fixing a t naught, right, you are looking at n t naught omega 1 over t naught, n t naught omega 2 over t naught, and so on, and your and this these different omegas have different probabilities, so to speak, as determined by the underlying distribution of these x's, right. Because little omega, what is this little omega? Once the little omega realizes, all your xi's realize, all your si's realize, right. So, depending on the realization of your inter-arrival times, you will have some particular realization of n t omega, correct, with me, and these little omegas have different probabilities, so to speak, right, and expectation of n t is like averaging over little omega, somewhat loosely speaking, correct, and for a particular t naught, n t over t is a random variable, you are taking expectation over that, correct. We are saying that if t naught is large enough, you first take expectation, right, you fix a t naught, take expectation of n t naught over t, that will be a number, right, for each t naught, right, that will be a number. Now you send t naught to infinity, okay. So, that limit is 1 over x bar, okay, that is what the elementary renewal theorem says, okay. So, you may, there is a t tending to infinity, of course, but it is first an ensemble average, it is an ensemble average, there is an expectation first, right. So, that is a different kind of a result, okay, and of course, the answers are the same, the ensemble average equal to time average, right. So, this property for nice processes, right, ensemble averages are typically equal to the time average, okay, and this property is known as ergodicity. So, you see already that strong law is a time average result, says time average converges to 1 over x bar almost surely. Elementary renewal theorem is an ensemble result, right, you are taking ensemble average. So, there you are saying that the ensemble average is also 1 over x bar. Okay. So, it is some sort of an ergodicity that you see here, right, that the time average is equal to ensemble average, okay, and we will repeatedly see this. Okay. If you will take time average, you take ensemble average, often for renewal processes or Markov chains under certain reasonable conditions, you will get time average is equal to ensemble average numerically, but the interpretations are very different. Okay. So, time average means something very different from the ensemble average, but if for nice processes such as these renewal processes and Markov chains which satisfy certain conditions, we will have them to be numerically equal, the time averages and the ensemble averages. Okay. This is a recurring theme in this course. So, I want to already point this out at the first instance when we see this to be equal. Okay. Of course, there are two very different results, right. It is I am not saying that because of ergodicity they are equal, I am saying that ergodicity follows from strong law and elementary renewal theorem, which are two big results by themselves, and hence we conclude that there is a certain ergodicity in the renewal process. Okay. All right, is that clear? Okay, so that is just a prelude. What I wanted to discuss today was residual life, age and duration. Okay, and we will discuss time averages. I will tell you what residual life is, I will tell you what age is, I will tell you what duration is, and I will help you calculate the time average residual life, time average age and time average duration. Okay. And you will not be surprised to see that when we do ensemble averages much later, the answers will be the same. Okay. But the reason they are equal will be more non trivial. Okay. We will use reward theory to to calculate both time averages and ensemble averages. So, I will tell you what residual time is. Okay. So, residual time, what is the residual time? So, let us say you have this renewal process, it starts at 0, okay. These x's are IID, you know what a renewal process is, and you take a particular time t, okay. What is the time instance of time epoch of the previous arrival? SNT, right. See, at t there have been NT arrivals. So, if you look back from t, the nth arrival whenever it took place, the epoch is nothing but SNT, right, and likewise this epoch is SNT plus 1, correct. Yeah. Now, I will tell you what residual time is. Residual time at t. So, you are looking at a particular t and defining the residual time at this particular time t. Okay. It is defined as Sn. So, Yt is the usual notation that is used in Gallagher's book, is simply S Nt plus 1 minus t. Okay. So, which is, so Yt is this guy, right. So, I am looking at, I am fixing a t, I am looking at the arrival before it and the arrival after it. So, Yt, the residual time at time t, is the time to wait for the next arrival to come after t. You are looking at a t, right, and the time to next arrival is the residual time. So, in a physical example, so this renewal process may be arrival of buses to a bus stop, right. You showed up at some time t, how long will you wait for the next bus? That is the residual time. And analogously, age is just t minus s and t. So, you showed up at the bus stop, how long ago was the previous bus? So, that is, so this this length is called zt, age, okay. This is age zt. So, it is called age because how old is the previous renewal, right, how long ago was the previous renewal, okay. And duration, so this is age at time t and duration at time t is nothing but so let us denote it as x of t, which is basically just y t plus z t, which is equal to s n t plus 1 minus s n t, okay. So, x t is z t plus y t, duration is age plus residual life is duration, okay. Is that clear? So, you are showing up at the bus stop at time t, how long is the duration between the previous bus and the bus you are going to see next, okay, that is the duration, clear. Any questions on this?
So, it will be same for all points between two arrivals, duration time will be same for all points between two arrivals.
Duration, yeah, you are right, right. If it so happens that there are no arrivals between t and t prime, then duration at time t and duration at time t prime will be the same. Of course, the residual life and age will be different, correct, right. If I choose some other t prime here, then the duration will be the same, but not age, and age will be shorter and the residual time will be longer, or the other way around, assuming there is no arrivals between the two, right, 2 times. But for a given t, this is clearly defined, right. Y of t is s n t plus 1 minus t, z of t is t minus s n t, and x of t is s n t plus 1 minus s n t, simple as that, okay. So, we in this one of the things we will do is to calculate things like what is your average residual life, what is your average age, what is your average duration, where the average could be time average or ensemble average, okay. Of course, they will turn out to be numerically equal, but the meanings are very different, okay, all right. So, we will calculate the average residual time, average age, average duration, time average, okay, and the answers will be the same for the expected value as well, the ensemble average as well. So, one thing I want to point out, and this will become more obvious later, is that this duration at time t, which is s n t plus 1 minus s n t, is not your typical renewal duration. Is that somewhat clear to you at this point? So, what I am saying is that this so what is this s n t plus 1 minus s n t is that is also basically this guy, right. So, x of t is nothing but x xnt or xnt plus 1 xnt plus 1 xnt plus 1, right, by where xi's are your renewal, I mean the IID random variables which define your renewal process, but this x of t which is x nt plus 1 is not, it does not have the same distribution as your typical xi intuitively. Why? It is a very special interval which contains t. Okay. So, it is not, we will see in fact that we will derive a full characterization of the distribution of xt's and yt's and zt's, but already it should be, you should get used to the idea that the interval in which you show up is an unusual interval. Okay, there are buses are running like a renewal process, let us say at a bus stop, you show up at the bus stop at some particular time, okay, and because it contains your arrival, your some exogenous person coming to that bus stop, that duration between the previous bus arrival and next bus arrival is not typical. Okay. So, for example, right, in a Poisson process, let us say, right, this is the most concrete example that we know of. Poisson process is of course a renewal process. So, you show up at time t, right. We know from memorylessness of the Poisson process that the residual time is exponentially distributed, correct. So, yt is an exponential with parameter lambda, whatever the process parameter is, and likewise if you run the process in backward time also it looks like a Poisson process. So, if you look at t, the time since the last arrival which is the age is also exponentially distributed, and because of this memorylessness you can argue that this yt and zt are independent for the Poisson process, generally not true, but yt and zt are independent for the Poisson process. So, yt and zt are both exponentially distributed with parameter lambda and they are independent. So, the entire duration between the previous arrival and the next arrival is distributed like a Erlang 2, sum of two independent exponentials, right. So, even in a Poisson process you are already seeing this, right. You have a Poisson process running, all inter-arrival times are exponential with parameter lambda, but you fix a t and you look at the time between the arrival before t and the arrival after t, it is not exponentially distributed, it is an Erlang 2 distribution. In fact, the expected value of the time will be how much? Twice as large as a typical duration, right, typical inter-arrival time, the duration is twice as long in expectation for the Poisson process. So, you are already beginning to see that the duration is not a typical renewal time. So, we want to know what is its distribution, you see what I mean, it is a very special interval which contains t, it contains your arriving at the bus stop. So, you do not know anything about the bus process, right, you just showed up at some time t, correct. So, let me I mean just to drive home this point, let me give you another example which may be slightly pathological, right. Suppose your bus inter-arrival times are very small with very high probability, okay, let us say epsilon, and very high with small probability, okay. So, you have a bunch of buses coming very close together and then there is a huge gap, right. In this kind of a situation, your the time t that you pick is very likely to be in the, see what I mean, right. If you just show up at this process, you are much very likely to show up at one of these long inter-arrival times. So, although the expected whatever the distribution of the time between two buses is very small typically, because with very high probability you get two buses very close together, the interval in which you showed up to the bus stop is very likely to be very large, right, which is probably why you feel that whenever you show up to a bus stop you do not get a bus for a long time, right. And in such a duration a lot of people show up to the bus stop. So, the bus in which you go tends to be very crowded, right. This is something that is this is known as sampling paradox. By variously it is known by various name. One name is sampling paradox. The bus in which you travel tends to be very crowded, right. Yeah, likewise even in social networks you see this kind of a phenomenon, right. You are likely to run into nodes with lots of friends and all that, So, anyway, so that is I just wanted to point out that this is a phenomenon that we will study in detail, and this xnt plus 1, which is the duration, is an atypical time between two consecutive arrivals. Okay.